Good night, everyone. Mechanics of Material, Chapter 5, Torsion. Torsion in shafts. Let's solve an interesting example in torsions in shafts. So we want to see if we have such configuration and a torsional torque applied at the free end, what is the tau maximum in such case. So shaft AB, it's located inside the tube CD, and the connection part is a annular plate like what you can see with the radius of R1 and R2. And then we want to see if we want to apply a torsional torque, what is the angle of twist between a BC solid shaft and tube CD, which is connected with this annular plate. So in this problem, we do have an annular shaft, an annular plate, what you can see here with the thickness of T. So this is our annular plate with the thickness of T and shearing modulus of G used to connect the shaft AB. This is shaft AB with the radius of R1, which is the same like internal radius of this annular plate, and to tube CD, this is tube CD with the radius R2, which is this one. Knowing that the torsional torque T is applied at the end A, so a torsional torque applied here in shaft AB, and at the end D is of this tube is fixed. We want to determine the magnitude and also the location of maximum shearing stress in the annular plate. In the annular plate, where is that, how much is that, and where is that, and also show that the angle through which end B with respect to C rotates is coming from this equation. So this is shaft AB, this is tube CD with this radius of R2 and R1. This is radius R1, and this is our annular plate, which is the connection between the solid shaft to hollow tube. And then we want to know what is the angle of twist between the solid one and the connection part. So let's approach our problem. If a torsional torque applied at the free end of solid circular shaft, it just transfer to the other end and it just goes to the annular plate. So because these two parts are fixed inside each other. So this is tau, this is R1, and and so the moment or torsional torque, if you remember, torsional torque is a kind of moment, and any moment is a force times the R. So our force is, if you remember, force is a stress times the area, and area for annular plate is 2 pi r thickness. So that's 2 pi radius thickness, and the r is also r1. We just call it r here for general term. And then if you rearrange the equation based off tau, it just gives you torsional torque over 2 pi thickness r squared. And definitely tau maximum is the tau maximum transfers from the solid shaft. So that's related to radius of solid shaft. So that's T over 2 pi R1 square times T. So that's why we use R1 here. We use like a general term, then refer to our solid shaft which the torsion applies or initiate there. So in such case, and also from the Hooke's law, in shear, we do know gamma is G over tau over G. If you remember, Hooke's law says sigma has a linear linear relation with epsilon, and that's in normal. and in shear tau is G times gamma. So gamma is tau over G, and we already know what our tau is. If we replace it in tau maximum for tau, you can get this equation. That's the gamma is equal to torsion over 2 pi G thickness R squared. So if we move to the annular plate, the relative circumferential displacement in radial length d rho is the radius. So if you take an element out of that, you can easily see the circumferential displacement. If you consider the internal one is r rho, and then change to d rho, and the circumferential displacement, if you call it like an arc like d delta, and this angle is our gamma, which is calculated in previous steps. So if you have an arc, this is r, this is theta, the arc is r theta. So the same concept, d delta is d rho times gamma. And at the same time, if you create a small angle like d phi over here, this is our phi, and this is the small elementary form of that, and it just create d delta. And if this distance is small enough, we can call d delta is equal at the both and down, the up and down both of them. So another relation base of d delta is rho times d phi is equal ds as well. Combine these two equation gives us rho d phi is equal to gamma d rho, and that gives us a relation of a differential relation, a relation for differential tangent or tangent of the angle of twist, which is d phi is equal to gamma d rho over rho, and d rho over rho is simply dr over r. So now we already know what our gamma is, and then d phi is equal to gamma d rho over rho. If you just plug in this gamma in this relation, it just gives you elementary angle of twist is t over 2 pi g thickness r squared dr over r. We just replace d rho over d rho. They are identical to each other. So I'm in this part. And if you just integrate it, it just gives you the angular change from b to c, which is phi b over c or phi bc, integration from r1 to r2 in the our annular plate. And if you do the integration, it just gives us the same numeric, the same parametric formula we were looking at. And then that's the answer of the change in angle of twist in our annular plate, which is the connection of solid circular shaft to a hollow tube CD, which is fixed at one end, and phi bc is then equal to t over 2 pi gt times 1 over inner radius squared minus 1 over outer radius squared. Thank you. We'll solve more problems.